Alright, welcome to a new segment. In this segment, we're going to look at linear models. So in general, linear models are typically IVPs, initial value problems. Actually, the equation itself is not dense at all. Alright, so this is what it's going to look like. K times X. And I have some kind of an initial condition, you know. So this in real life is applied to multiple things. For instance, if I have, let's say, a petri dish in here, and in a petri dish, I have this bacteria, right? And let's say that at t0, I start with a particular number, and you can see what will be the number at a different hour. Let's say 1 hour passes, 5 hour passes. So as long as I know this k value that I have here, right, I will be able to obtain myself what will be the population of this bacteria at a given certain time. So it's fairly straightforward. But the good news I want to share with you in this here is the solution of this equation is actually fairly easy compared to what we have been dealing with. Okay, the applications are exciting, they're from real life, so that's good, but it's not really dense, so that's a good thing about it. Okay. The other thing, in addition to this growth and decay applying to bacteria or small animal population, we also have a half-life. I'm sure you heard about that one before, right? So what it simply says that it measures the stability of a radioactive substance, and it looks at what the time it takes for radioactive material to lose half its weight. It can be disintegrate, as an example, into other elements, right? And the longer the half-life is, the more stable that particular material is. Okay, as an example, let's give radioactive radium. Okay, so this is radium 226, and the half-life of it is about 1700 years. So it just take let's say that I start with a particular amount, so it will go half of it will be stay after I reach 1700 years, but the other half is actually will be converted to radon. It's radioactive as well. The most common uranium isotope is U-238. Okay, and the half-life of it is a little bit higher than this. What is it, 2000 then? 5000? 10,000 years? No, it is 4.5 billion years. Okay, so it's a little bit higher than that, right? So obviously, as the definition says, half-life, so it's going to be half of it will be remaining as this. And actually, even interesting thing is it goes into lead, right? So that's not good at all, right? I mean, whichever angle you look at it, right? Let's go here and say half-life, right? You can read more about it. The next thing, this is also related to half-life, is it's kind of interesting actually, this particular one. It's called the carbon dating. Carbon dating. So what this particular person, his last name is Libby, and he actually got the Nobel Prize for Chemistry in 1960s from this technique that he developed. So what he looked at is there's a carbon-14, so this is a radioactive isotope of carbon, okay? And he looked at it, the ratio of this C14 to C12, and when somebody passes away, there will be no exchanging, breathing, eating, or photosynthesis. So those all actions will cease. So looking at the ratio of C14 to C12, you can kind of estimate the date, and you can use it to date. For instance, wooden furniture in Egyptian tombs has been used. Okay, so the only thing that you need to know about it is the half-life of it is 5,600 years. All right. So in 5,600 years, the C14 will go half of it. Right. So actually, I want to apply this because, well, it's easy, but let's find out when we do it. So let's call this dA dt minus Ka is equal to 0. Okay, so this is basically, I reshuffled this and I, looked at X is equal to A, right? So you can see I get this for carbon dating. So why don't I obtain this constant of K here, right? It will be good to have this because it's a constant value, right? This equation is actually very, very easy to solve, so I will not demonstrate it now, but it's a separable equation, right? I have solved this equation in the separable section, so I will go ahead and write the answer to you directly, but just, it will take like 1 minute, so you can go ahead and try this, okay? So I'm gonna get myself A as a function of t will be c, which is a constant, times e to the kt, right? So the thing is, I have a initial condition in here. It's at 5,600 years, right? I will obtain half of it. If let's say that at t is equal to 0, I have a 0. At t is equal to 5,600, then I will get a0 over 2, right? So I have two, you can see as a function of time, I have two conditions on over here. So if I just plug t to 0 over here, what will I get? So you can get that a0 is equal to c times e to the power of 0, which is 1, right? So I get myself c is equal to a0 then, all right? And if I use the second initial condition that I have here, then I plug the same way up there. So I will get myself a0 by 2, right? And let's, as c is equal to a0, so I can write a0 here times e to the power of k times time is 5,600, right? So you can see this is 1/2, right? So these cancel. I get myself 1/2. And if I take the ln of both sides, you know I do this a lot, right? So I get myself ln of 1/2 will be equal to 5,600 times k, right? So if I go ahead and plug this into my calculator, I will get k is as 0.000 negative, obviously because it's a decay, right? 78. So this will be the k value. So if I want to write this a of t, a0 times e to the minus 1, 2, 3, 1, 2, 3, 7, 8 t. So this will be the equation that now you can apply for Libby's carbon dating. Okay, but you know, just want to highlight that there's also Cambridge half-life. You know, they have modified this slightly, and they call this half-life as 5,730 years. Okay, that's fine. It's just a different take on this whole thing. While I'm at it, I want to just go ahead and apply this to a particular dating that has been used. All right. So what I'm gonna pick up is actually Shroud of Turin. Okay, so this is religious significant. You can read on that one, but that's beyond the scope of this particular mathematics course. But in 1988, Vatican gave permission to have this Shroud of Turin to be dated, right? So they have done some independent laboratories have dated it, and they find it to be approximately 660 years. Okay, so the question that I want to investigate in here is, if I'm using this half-life, where is it? Right here, carbon dating, right? So what percentage? You see that half of it will be gone by 5,600 years, and I'm at 660 years. What percentage of carbon-14 will stay? So you can see that this is 660, and the half-life is 5,600, right? So let's go ahead and investigate this. What percentage will stay? Okay. So actually, once I do the trick that I did up there in terms of finding my equation, well, it's fairly now doable, right? So my goal is to get this a of t. That's the question after 660 years. That's divided by a0, right? Because just to get some ratio, because that's what I'm interested in. Minus 0.123, well, 12378, and t I'll insert 660. So when you do this, you're gonna see that you're gonna get 0.99. Just punch into your calculator, 22, give or take. Okay, so then you'll see that after 660 years, right, this C14, 99.22% staying. Okay. So now I want to illustrate you something. Sometimes I see this in the exams when I ask a question from this angle. When students hear linear, they think that the solution is linear. I'm not talking about the solution. I'm talking about the equation. Okay, because the title of this particular segment is linear models, right? As it's linear models, I'm talking about this equation to be linear, right? But I'm not talking about the solution, So for instance, if I really plot this, if I wanted to, you can see that this is right around what? I don't know, let's say 12% or something. 12%, right? Give or take. I'm sure this is about that. So 12% of this, but then I only lost 0.78%, right? So what this means is, as a function of time, if this is t and this is the C14 that is remaining, So you can see that it's like this, something like that. Okay, so you can see it's highly nonlinear. Just want to highlight this. Okay,